Okay, in this segment on tensors, we are going to look at some properties of tensors. Okay, so we are going to look at properties of tensors. The first sort of subtopic we will look at here are just some elementary properties of addition of tensors, right? So tensors have this dominant property of linearity, which we've already seen to some extent, but let's understand that in a slightly different way. Okay? Tensors are linear. What this means is the following. Supposing we were to consider, supposing we say that tensors A, B, C are all tensors of the kind that we've just seen. So that means that they all belong to this mathematical space that we are calling GL3. Okay? We may ask, what do we mean if we write a tensor C to be alpha times A plus beta times B, where alpha and beta are just real numbers? Okay? So we may ask what we mean by this. To understand what we mean by this, we just look at the action of this tensor on some vector. Okay? So to understand what this means, we consider C acting on U. Okay? So C acting on U should be alpha A plus beta B acting on U. And to define this action, we say that this is simply alpha AU plus beta BU. Okay? So this is what we mean by the addition of tensors as well as by the scalar multiplication of tensors, right? So we've multiplied a scalar alpha into a tensor A, and likewise a scalar beta into a tensor B. If we ask what do we mean by this, well, what we mean by this is the result on the last line. Okay? With this sort of a property, what we see is that many other things also follow. Okay? From this sort of an idea, it follows that, for instance, if we write A plus the 0 tensor, this is equal to A, right? And this is the identity of addition. Okay? And what this also tells us, of course, is another way of writing the same result is A plus minus A equals the 0 tensor, right? This is the nullity of addition. Okay? In fact, if we just continue working through this sort of an idea, everything coming from what we wrote on the top under saying tensors are linear, what we will observe is that tensors actually have many of the same mathematical properties of addition as do vectors. Okay? So They also have the same properties of scalar multiplication. Okay? So also the same properties of scalar multiplication as vectors. Okay? And in fact, for this reason, tensors are said to actually form a vector space themselves, where now vector space really refers to these properties of addition and scalar multiplication that we know that conventional vectors in Euclidean space have. Okay? So we say, for this reason, we say that tensors themselves form a vector space. And here the idea of vector space should not be considered with the actual Euclidean vector in 3 dimensions, right? But here vector space refers in particular to these mathematical properties of addition and scalar multiplication. Okay, so that's just an aside. Okay, so let's press on with this idea of particular properties of tensors. We're going to look at a few of these properties, by no means all of them, but some of them that will be relevant to our study of continuum mechanics. So the first property that we will consider is this property of the transpose of a tensor. Okay, so if we have a tensor A, we will denote its transpose by A transpose, and in other sources that this is sometimes written as A star or A prime and so on. We will write it as A sup T for A transpose. In order to define the transpose of a tensor, we will do the following. If we have A transpose act on a vector U, we know that gives us a vector. If we dot it with another vector V, we can ask what we mean by this operation that we've just written. And what we mean by this operation is simply U dot with A V. That is what we mean by the transpose of a tensor. To see how this works out more specifically in terms of the components of A transpose, we repeat this operation by using basis vectors EI and EJ in place of V and U. So we simply write this as EI dotted with A transpose EJ, and this is, being careful now, EJ dotted with A acting on EI. The right-hand side we know already, right? We saw a few slides ago, we saw in the previous segment what the right-hand side means. The right-hand side actually turns out to be the AJI component of our tensor A. But then following that sort of convention, on the left-hand side we have A transpose. Again, I'll just put parentheses around it and say that, well, this is the IJ component of A transpose on the left-hand side. Right? Just recognizing that A transpose also is some tensor. Right? So EI dotted with A transpose EJ ought to be the IJ component of A transpose. If we ask then what we mean by the IJ component of A transpose, well, it is just the JI component of A. Okay? So this is what we mean by the transpose of a tensor. Okay, pressing on then, let's look at some other properties. We will look at the idea of the multiplication of tensors. All right. In particular, we can write C equals AB, where everything is a tensor belonging to GL3. Again, we may ask what we mean by this. Now we're probably getting fairly good at answering this question. In order to answer it, we just need to consider, well, what does this mean in terms of components, right? And to do that, we carry out an operation on the left and right that we have already done a few times, right? So we will write EI dot C EJ. Again, I'll put parentheses to make very clear what I'm doing. Okay? So that's EI dotted with AB EJ. Okay? All right. To proceed from here, we can now write the right-hand side as EI dotted with A acting on B EJ so that's A EI dotted with A. Now we recognize that B EJ is a vector itself. Following our convention that we've already established, we write that as B KJ E sub k. All right, that's how we're writing B EJ. So we have now EI dotted with, I should probably put parentheses up here. Okay, so we have EI dotted with A EK, all of this multiplying B KJ. Again, using the linearity of vectors. All right. Now, BKJ is after all just a scalar, right? Because it represents a bunch of scalars because those are just the components of B. But look at what we have here now. We have EI dotted with A EK. We know what that is. That is A IK B KJ. All right. We did nothing with the left-hand side all along, and we didn't need to do anything to it, but now we can, right? Because now we observe that the left-hand side, which always was EI dotted with CEJ, we know that, well, that is just CIJ, right? And here we have our result for C equals AB expressed in terms of the components, right? Cij is just Aik Bkj. Now, of course, you recognize this as a particular manifestation of your well-known rule of matrix multiplication, right? On the right-hand side, it is K that is being summed over. Correct? And so we have Cij equals Aik Bkj. If you were to write it out in terms of matrices, right? The matrix representation in terms of the components is just this, right? We have C11, C12, C13, and so on until we come to C33 equals A11, A12, A13, and so on to A33 times B11, B12, B13 up to B33. So, when we have the benefit of a basis, our rule for tensor multiplication essentially reduces to the multiplication of matrices from linear algebra. Okay? We continue with more ideas of tensor multiplication. we will look at what we will sometimes call the scalar product of tensors. Okay. Also sometimes called the contraction of tensors. So, if we have tensors A and B, we will write the scalar product of A and B, or the contraction of A and B, with that symbol, the colon symbol. Okay. So, A contracted with B is how I will often read it. A contracted with B is simply the product Aij, Bij. Okay. Both indices I and j are repeated, so there is a sum implied over both of them. Think about it for a second. Think of what kind of object we get here. We observed that the multiplication that we saw on the previous slide led to a tensor, right? What does this type of multiplication lead to? Right? It leads to a scalar, if you were to carry this out, right? So let's say it leads to a scalar, let's call it alpha, which belongs to the real numbers, right? So the scalar product of tensors, or the contraction of tensors, leads to a scalar, and hence we call it the scalar product sometimes. Two more properties that we look at today. The fourth is this idea of the trace of a tensor. Okay, so the trace of a tensor A, we will write it as TR of A, okay, can be written as simply A I I. Observe that the index I has been repeated, and therefore there is a sum implied over it. This simply works out to A11 plus A22 plus A33. Okay. If you were to carry out the calculations, you will discover that the trace of a tensor is invariant with respect to basis. The fifth property we will look at is what we call the determinant. Right? The determinant of a tensor. Okay? So, we will denote it as determinant of A. Now, you've seen that when we have the benefit of a basis, we can represent a tensor essentially as a matrix. Well, you also might expect that the determinant of A ought to have some relation to the determinant of a matrix, and indeed it does. The determinant of a tensor A is simply the determinant of the matrix representation of that tensor in a given basis. Okay. The expression for a determinant can be written out in terms of our permutation symbol that we introduced a couple of segments ago, and that relation is the following. The determinant, you may recall, is cubic in the components, right? If it's cubic in the components of the matrix. So the same thing happens here. 1/6 of this quantity is the determinant of A. Okay? Observe what's happening here. We have AIL, AJM, AKN multiplying epsilon ijk, epsilon lmn. If you look at this carefully, you will observe that every single index is repeated. So the result is a scalar because there is a sum implied over all those indices. Okay? So this is how we write out the determinant of a tensor. When we come back, we're going to end the segment here, but when we come back, we're going to look at a couple of more properties of a tensor that relate to vectors as well.